So first of all, there are not 42 slides that I'll read to you. So I'm very lazy. This is the talk that I've given many times in the fall of 2015, and it has an upper bound of an hour. So I just do the slides that make sense here. So, you know, just complete laziness. Okay, so let me tell you the context of this a little bit. So actually, in 1991, I was visiting CORE. Lawrence may remember this, that I was there. And I gave a talk on this topic here. And I think actually Monique saw this talk in Amsterdam that year. You remember the talk, of course. All right, so it doesn't matter. No one really remembers this, whether they were there or not, so that's good. So I'm going to talk about some old work that I did on comparing polytopes by using volume as a measure. Talk about just some kind of computational results that motivate this, even though it occurred afterwards, and then talk about some more recent work motivated by what's called spatial branch and bound, which is a method for global optimization, also related to comparing relaxations by volume. So now I skip some slides that are meant for a general audience. Okay. So you're supposed to be flattered. You're experts. You didn't need those first slides. Okay. So I teach integer programming sometimes. And one of the simplest modeling examples that I give, I'm sure many of you have done this too, is uncapacitated facility location. So you have facilities, n of them. There are indicator variables for whether a facility is operated or not. There are fixed costs for operating the facilities. Then you have these xij variables. Xij is the proportion of customer j's demands satisfied by facility I. So you make sure each customer has all their demands satisfied. And then somehow you need to link these shipment variables to the facility variables. And so you use one of two possible methods to do that. So there's the so-called strong formulation, where you say that each xij is less than or equal to yi, and sure enough, if yi is 0, it shuts down all of the xij's for that I. Another way to do that is with a big M, which we use as little n here, which is just the sum of these strong inequalities over n. And this has the same effect. If I shut this variable down, turn it to 0, it shuts off all these variables. So, you know, it's obvious that the strong formulation is tighter than the weak formulation. And if you generate, you know, a random problem with, I don't know, a couple of hundred customers and 30 facilities with random costs and linear shipment costs, what you'll find is the strong formulation very often has integer solutions, and the weak formulation is complete crap. That what happens is these y variables cheat, and they set themselves to very small fractional values, and you start branching forever, and the weak formulation is terrible. The strong formulation is quite good if you really want to solve problems with linear objective function. And so an interesting question is that intuition, does it hold if the objective function is not linear anymore? So this is a plot where I look at objective value for different formulations where I have linear costs, but also quadratic separable costs. So the f is xij squared with a constant in front, and you can go and solve this problem. The weak relaxation with these inequalities, the strong relaxation, and the integer program itself. So if you do that, this is the kind of things you see. Now what I have here is I fix the number of facilities and I solve the problem for different values. So this is the linear world. And the optimal integer solution is the yellow curve for different numbers of fixed facilities. And what you see is just what I said before. The strong formulation, you can't even tell the difference. It often gives you the integer solution for free, or very little branching will get you there. And the weak formulation really is terrible, especially for small numbers of facilities. For separable quadratic costs, so you have a convex quadratic, you get a very different behavior. So the yellow curve is the optimal integer solution, and you see the weak and the strong are about the same. So what it seems to tell you is that if you're interested in solving nonlinear objective functions over these facility location formulations, the type of objective function you're looking at matters. it probably shouldn't be using the strong formulation in certain situations because it's heavier, it's more inequalities, the LPs will take longer to solve, and you're not getting anything better on the bounds. So you can actually see this borne out with computations with actual solvers. If you do branch and bound for a linear objective on the weak formulation for one random problem, there's a significant amount of branching. It takes some time. With a strong formulation, there's no branching at all. For the quadratic problem, you can see a very different behavior. The weak formulation maybe has somewhat more nodes than the strong formulation, but the total time is actually worse for the strong formulation because those relaxations take longer to solve. So this is, in a way, by motivation, the idea of trying to come up with measures of quality of a relaxation that are independent of the objective function, and the natural measure would be the volume of the polytope. Because this sort of corresponds to a uniform measure where the optimal solution might occur over the whole relaxation. At least that's the story I'm telling. So here's the measure we use. You can think of other ones too. But what we do is we take the volumes of the two relaxations and we compare them this way. We normalize by the volume of the unit ball, and we take the dth root and subtract. What this corresponds to, if I have two polytopes, say one contained in the other, it corresponds to looking at the two balls that have the same volumes and thinking of them as concentric and looking at the radial discrepancy. So it's like objective gap in a way. But it's not really objective gap because I'm not integrating over all possible linear objective functions, for example, but it's in the units of objective gap. Often we're thinking about problems in the unit cube, and so what we're thinking about are that this measure might be as bad as square root of d, and so it's interesting for different formulations to see when it is really as bad as square root of d or when it's a lot smaller. Okay, you can think of other ways of taking the volumes of these two things and combining them. You can look at the ratio. You can do whatever you want. Okay, that's not my business. That's up to you. Example, the facility location problem again. So I'm going to take the essence of the facility location problem, which is those forcing constraints, and try to analyze what the volumes are of these two sets. So forgetting about that the demand has to add up to 1, that is not really the essence of the problem. It's these forcing constraints. So this is the strong formulation. Really, it separates by facility variables. So, well, we'll get to that in a second. But what I'm going to do is compare these two formulations: the strong formulation for the forcing constraint and the weak formulation. So it's clear that this strong formulation sits inside of that, and the question is, how do these volumes behave? So this is how they behave according to this measure. So if you look at this, what I call the idealized radial discrepancy, you have a nice closed formula for it. The proof is completely elementary, so let's just see how it goes. So the strong formulation, it's just the cross product of m copies as m facilities for each of these. Right, I've just suppressed the I variable, and for each facility, it's just, this is what the set looks like, and it's just the cross product of all these. It's really easy to get the volume of this. So this sits in dimension n+1. These inequalities are the inequalities of an ordered polytope. So you have a partially ordered set. The partial order is just what you see here, that each xj is less than or equal to y. And the volume of an ordered polytope is just the number of linear extensions of the partial order. It just corresponds to the number of different orderings of the customer variables. There's n customers, so there's n factorial orderings, and so the volume is just n factorial divided by the dimension of the space factorial. So the volume is 1 over m+1, but we have the cross product m times, so that's the volume. Easy enough. If you look at this other set, for the weak formulation, it's maybe slightly more complicated to try to understand what the volume of that might be, but it's actually also quite easy. So think of this as a subset of the whole box. So that's the box for all the variables. And so I want to think of this polytope here. Also, it's just the cross product of m copies, 1 for each facility, but this is the essence of it. And I just think of this as the box intersected with that one inequality. And, well, you can see if you make an affine transformation taking every variable into its complement, that's a unimodular transformation, and actually takes the box into the the partial box into the other side of the partial box. So that means that inequality splits the box into two. And so the volume is just a half, and there's m copies, so it's just 1/2 to the m. So really elementary proof of that. But doing some asymptotics on it is interesting. So if you let the number of facilities grow like log of dimension, so I turn this into a one-parameter problem of dimension, and let n grow like the dimension over log dimension, then this discrepancy goes to 0, actually. So what it tells you, these polytopes asymptotically, in this regime at least, are getting very, very close. And so that's one possible explanation, or at least it correlates with the fact that we saw that this weak and strong formulation really aren't too different in this sense. Just, to highlight, that this isn't telling you, yeah.
So I guess I'm a little confused by that takeaway that shouldn't we then have seen that convergence also in the linear graph?
So what you see in the linear graph, I think what you're seeing is this, that if you look at the worst case objective discrepancy, so that's this, I look at different objective functions and I look at the objective discrepancy, it actually can be quite large. And so somehow what's happening is there are lots of cases, if you were to average them, this is the worst case, but if you somehow integrated over all objective functions, you would see something a lot worse, I think. So I think that's what's going on. But again, that was kind of a motivating example, and I want to kind of just get away from an objective function and just think about something that's objective-free. So I think this somehow correlates with that motivation. There's a lot more in this paper. So we looked at a lot of combinatorial polytopes, and like vertex packing on very special graphs even, like if you know what a threshold graph is. And you can show, you can get lots of interesting comparisons of different models for the same problem. So that was just kind of a sample result, but you can find more of this in here. Then, I continued with this for a while, looking at relaxations of the Boolean quadratic and cup polytope, and then I got bored. And Einar Steingrensen continued this a while, and then he got bored, and that was kind of the end of that by the mid-90s. So at the, no, well, I won't say that. So now I want to come to the second part, which is modern times. So if you want to actually solve global optimization problems with software, like you use a modeling language like AMPL or GAMS, and then you want software to solve your global optimization problem and not have to do too much work, you use packages like Baron, Quen, and Skip. These packages are all aimed at what are called factorable problems. So a factorable integer nonlinear program means that you have a library of basic functions, you have convexification rules for those basic functions, and every function in your model is built up from basic functions. So, for example, you might have, most of the basic functions are functions of one or two variables. So you have functions of one variable like sine, log, you have functions of two variables like product and power, and you need a convexification scheme for each of these. And then what the methods do is they build, for every function, a decomposition directed graph. So you start with the function you're trying to decompose. I'll show you an example in a second. And you start decomposing by these basic functions, and so you get this kind of tree or really directed graph. And then what the methods do is at the bottom you have the atomic variables. Atomic variables have ranges, usually, domains. And what you do is from those bounds on the atomic variables, you can infer bounds higher up in the tree, and then you can actually go back and forth. And so what the method does at the kind of at one level is refine bounds by moving up and down the tree. But eventually, you solve a relaxation based on these decomposed functions, and you find that it doesn't satisfy all the original equations and inequalities. So you want to refine these convexifications. And so the way you do it is you split the domains of these atomic variables, and you reconvexify, and that gives you tighter domains on the functions higher up in the tree. And you just keep doing this, and you do, what's called branch and bound based on this. So that's the general idea. But there's some choice in how you do things. So if I have a function like x1 times x2 times the sine of x1, x3, well, at the first step, I could decide to view this as the product of x1, x2, and the sine. So I decompose that way. And then there's really not much choice. x1, x2 is the product of x1 and x2, and the sine I pull out, and then I have x1 times x3. But at the top, I could have made a different choice. I could have first associated, say, x2 with the sine of x1, x3, and decomposed this way. And then, well, there's not much choice after that. Or I could have put x1 with the sine of x1, x3. So there's different choices, and software has to make a choice about how to do things. And the question is, does it matter? And if it does matter, can we get some guidance mathematically as to what's the best way to do things? So this is what I'm going to analyze for the case of the product of three things. So here, the three things are x1, x2, and the sine of x1, x3. But I could think of sine x1, x3 as a new variable y3. And so really, it's the product of three things. And I want to know, can I take information about the bounds on those three things and decide which ones I should associate first? So blah, blah, blah. Focus down here. So I have three things. We'll call them variables. And they have bounds, ai to bi. I'm going to assume for huge combinatorial convenience that these are non-negative numbers. The combinatorics gets much messier if we have mixed signs. So the first thing I'm going to do is relabel the variables so that this holds. To see that you can do that, for each I equals 1, 2, or 3, I can define this number. It only depends on I because j and k are symmetrically treated. So I have these numbers OI. I can order them 01, 02, 03, and that corresponds to relabeling the my thumb is too fat. Relabeling the variables so that this is the case. So for the rest of the talk, I assume x1, x2, and x3 are ordered so that this inequality, these two inequalities hold. And that's going to matter. Trilinear monomials, the product of three things, has been studied quite a bit. The convex hull of the solution set. So when I think of the solutions, I think of four variables. There's x1, x2, x3, and then the top variable is the product. So these are the different combinations of the variables at the endpoints of their ranges. So there's 8 possibilities, and then the top coordinate is just the product of the three variables. So if you want the convex hull of, if you want to describe the points f equal to x1 times x2 times x3, where the x's are in their ranges, that set of points, the convex hull of those points is the convex hull of these 8 extreme points. And you can make 8 variables, lambdas for these, add them up, say the lambdas add up to 1 and are non-negative, and then you can do Fourier-Motzkin elimination and get rid of the lambdas and get inequalities just on the 4 variables here. So if you do that, you get a big mess. And so this is, in Meyer and Floudas, you get this huge mess. Now, maybe software uses these kinds of inequalities. Maybe it doesn't. In fact, some softwares like Antigone uses these. Other ones like Quen don't use these. So what does Quen do if it doesn't use these and it sees the product of 3 things? What it does is it does McCormick twice. So what McCormick means is I look at just 2 variables now. So they have their ranges, and I want to model f is the product of these 2 variables. And what you do is you just write all these differences of variables and their bounds, and you multiply them together in the possible combinations These things are obviously non-negative. And if you multiply these out and then replace x1 times x2 with the variable f, which is supposed to denote the product, you get the McCormick inequalities. So I haven't really quite written them here, but the McCormick inequalities are just take these obvious inequalities, multiply out, replace x1 times x2 with f. Those are the McCormick inequalities. It's just the 4 inequalities of the tetrahedron of the 4 points. Oh, yeah, they're there. I don't see black. I only see red. That's right. I don't know. Been looking at this too long. OK, so what does software use if it doesn't use this mess? So there's some codes like Quinn and I think Skip that actually don't use this. So what they do is they do McCormick twice. So they take the product of the 3 variables, and they first write, f is w times x3, but then w is x1 times x2. So here's McCormick for x1 times x2, and now here's McCormick for w times x3. So software does this. People do this too, humans. Okay, so there are humans who use modeling languages to formulate optimization problems, and sometimes they have products of 3 things in their model. And so what they do is they often do this. They write this down. Believe me. These are actual humans that actually try to solve problems. The question is, though, I did this by grouping x1 and x2. If I'm a human and I'm going to do this, should I have grouped x1 and x2, or should I have paid attention to the bounds and grouped them a different way? And maybe I get a different kind of performance. So to really compare, what I'm going to do is get rid of the w variable. I'm going to project it out, because w has a meaning. It's x1 times x2. If I group things a different way, w will mean something different. So I should really, to compare, get rid of w. So if you just do Fourier-Matsky elimination, it's really quite easy here, because you know the signs of everything. So if you do it, you get this pretty simple system. I doubt most people would write this down. They'd probably write this down, but they could just as well write this down. It's not so hard. So now what I want to just do is analyze what's the best way to group the terms, comparing the volumes of these kinds of sets. And I want to compare it also to the volume of the convex hull of the 8 points. So blah, blah, blah. So I'm going to call the 3 polytopes P1, P2, P3. P1 means group x2, x3 first, do the double McCormick, project out the auxiliary variable w. That's my set P1, similarly for the others. So the subscript is the variable that's not being grouped. So I want to compute the volumes of those 3 sets and the volume of the convex hull of the 8 points. So here they are. That's the volume of the convex hull. That's the volume of P1. That's the volume of P2 and P3. P2 and P3 look quite similar, and it's true by relabeling, it turns out they're essentially the same combinatorially. But P1 is different. So proof by missing 5. There's 5. There's no 5. Okay, so these really are different formulas, and the combinatorics is different. Okay, so I want to give you an idea how the proofs go. But once you calculate those volumes, you can actually see that P3 is the best. You should group 1 and 2 first, according to that ordering of the parameters. If you want the double McCormick that gives you the tightest relaxation, it's P3. But more than just knowing the ordering here, sometimes it might make sense to actually use the convex hull inequalities if the volumes are quite different. So these are things you can actually, you have formulas now. So in the code, or a modeler could actually evaluate these volumes and then decide what to do based on what they see. Usually, you should either use P3 or the hull, and if they're very close, probably you want to go and use P3, which is simpler. And if they're very far apart, then probably you want to use the convex hull inequalities. Blah, blah, blah. If you're curious, if you just have binary variables x1 and x2, so between 0 and 1, and you're interested in what the worst case is, if you fix B3, the upper bound on x3, the worst case difference in volume between the P3 and the other ones occurs when the lower bound is a third of the upper bound. That somehow is the worst case. Blah, blah, blah. So here's sort of how the proofs go. So we think of the usual four-dimensional cube, and what I'm going to do is take those 8 points and kind of try to visualize them. So the fourth dimension, the top one, the product of the four, is this outer one. So it's when you go from the middle cube to the outer cube, that direction is that variable that's the product of the three variables. So the V2, this point that's sitting on the inner cube there with everything at their lower bound, so that's where the three variables are at their lower bounds. And then the point where I put the point where the three variables are at their upper bounds is out here. Okay, so it's out on the outer cube, but then everything's at the upper bounds instead of the lower bounds, so it's the sort of outer point of the outer cube. And that's, you know, a reasonable place to put the other points to try to kind of start to see what's going on. So we've got these 8 points that are the extreme points of the convex hull in 4 dimensions, and we want to go and calculate the volume. So let me just skip over to here. So here's what we do. We grab 5 points, these 5, that form a simplex. Okay, so we pick 5 that are affinely independent. They form a simplex. It's easy to get the volume of a simplex by a determinant calculation. Okay, now don't forget, these points aren't fixed points, right? They depend on the parameters. So I have to check that these 5 points really are affinely independent for every choice of the parameters. But then I go and I calculate a determinant, and I can write down the volume. So now I take another point. V8 is that one. And I look at the simplex of the first 5 points, and I want to know what facets I see of the simplex. Because whatever facets I see, I'm going to build a pyramid over that facet. And those pyramids will be simplices themselves, and I'll be able to calculate their volumes and add up. So what I've got to be able to do is look at this picture and see what facets of the convex hull, the blue points, does that red point see. That's not really easy. If this was a 3-dimensional picture and I had it on the 2-dimensional surface, that would already be hard. But it's really, you can fool yourself into thinking you see something, but you don't, because you've projected out 2 dimensions here. But nonetheless, these pictures are a good crutch for trying to figure out what you need to do. So we have to figure out what that point sees. I'll get into kind of the details of that in a little bit, very little bit. Lower bound getting close to upper bound. But you just kind of keep repeating this, and you build a triangulation of the whole polytope this way. So that's really how you do it. Now, the hull is one thing. I know what the extreme points are. For the other 4 polytopes, P1 and P2, P3, I don't know what the extreme points are, so I can't exactly play this game. So, I wanted to just say this quickly. The kind of proof that I just did works when the AIs, the lower bounds, are positive. Okay? If the lower bounds are not positive 0, the combinatorics changes a little bit, but you don't have to do the combinatorics again. What you can do is use the fact, and I just really wanted to say this in this room, use the fact that volume is a continuous function in the Hausdorff dimension. And some other facts about convex hull being continuous in the ordinary sense, that you can put this together and see that really the volume formulas have to be correct when the lower bounds are 0. So the rest of the proof, to figure out the volumes of P1, P2, P3, you have to know what the extreme points look like. So here's what they look like. Each of the polytopes has the original 8 plus 4 more. P1 has these 4, P2 has these, P3 has these. There's new parameters, there's thetas. That's what the thetas look like. So, you know, why should you believe me? Well, here's the thing. What we did was we did a lot of computation to guess these formulas, okay? So a lot of computation to guess these formulas. Once we had these formulas, then what we start doing is compute the convex hull of these 12 points now for each of the P1, P2, P3. And we do the same thing. We see what sees what, and we go through all this business, and we build up these convex hulls. And at the end, we have the facets of the convex hull of these 12 points. And lo and behold, they're what we wanted. They're the inequalities of the double McCormick with the W projected out. So calculating the volume and establishing that these are the extreme points come together as we build the triangulations of the convex hull of these points. But you have to guess the points first. So that's the overall structure. Let me just mention one more thing. When you do this, at various points you have to plug numbers into inequalities. But they're not numbers, they're points like this. You plug them into inequalities and you have to ask yourself, does that point satisfy that inequality? You need to know that to know what facets a point sees of the convex hull you've already built up. So when I plug one of these things in, I'm plugging a formula, which is essentially a polynomial. The denominators don't really matter because they're positive. So I'm plugging in these polynomials into inequalities where the coefficients are polynomials. So what I get to check whether an inequality is satisfied by a point, to know what facets I see, I have to check whether various multivariate polynomials are non-negative. How are you going to do that? Well, so you're going to try to see if they're sum of squares. For many of the ones that you have to do, you can do it that way. But there's some that are just not sums of squares, and so you need ad hoc arguments why they're non-negative or not. So that's how it all works. If you want to see more, it's in this paper with my very talented graduate student who will need a job in 2 years, Emily Speakman.
Thank you, John. Time for a question. Any question?
No, I don't know. So it would be really interesting to look at families of objective functions. And then the natural thing is to integrate over all the choices of objective functions in some, bounded family of objective functions. I know some results for linear functions, but not for families of nonlinear functions. It's just, I think things get very messy. So I don't know. So, I mean, you could certainly doing the same for multilinear, not just trilinear, would be really interesting. We tried a little bit, I wouldn't say to the point of exhaustion, but there's some hope to do it for multilinear. The other interesting thing is if I have lots of trilinear terms using the same atomic variables, it may make sense to do things in a different grouping because you see the same pair twice often. Oh, by the way, so trilinear, you may say, well, what model is really a trilinear? But anytime you're multiplying three things, this is relevant. And in a past life, I worked for a large microelectronics company, and they had huge models for microelectronics imaging that had trilinear terms. So if the convex hulls of the relaxations are polyhedral, I think there's hope. If you get into situations that are not polyhedral, then I think, after univariate, you probably can do things, but after that, I think you need to be good with calculus.
Okay, so maybe we should defer further questions to the lunch break. So let's thank Jon.